So welcome to lecture number 31 of the Statistical Thermodynamics for Engineers. So in this particular course, in this particular lecture, we are going to look at the spectroscopy of diatomic molecules. So spectroscopy of diatomic molecules. Okay, so we presented a quantum mechanical analysis of the energy modes for a diatomic molecule. A significant aspect of this analysis was the full separation of the rotational, vibrational, and the electronic energy modes. So we saw there was a full separation of rotational, vibrational, and electronic energy modes. Great. Okay. This was successively implemented. What did we do? We implemented the rigid rotor model. Okay. Then we did the Born-Oppenheimer approximation. And of course we had the harmonic oscillator model. Okay, so we therefore expressed that if this is the internal energy, remember the external energy was all translational. So the internal energy is written as electronic plus energy due to vibration, energy due to rotation. Okay, the uncoupling, uncoupling of internal energy modes, okay, is a rudimentary model. Okay, and it provides a simplest explanation for its various spectral features that we will see. Okay, so this is now, if we convert this equation now, okay, to the units in wave number, so convert to centimeter inverse, which is basically your wave number. Okay, so the internal energy is written as dE plus GV plus Fj. Okay, so these are the three different energies that we write it in terms of the wave number units. So this is a simplistic model, which provides a simplistic explanation also for the various spectral features that we might have. Okay, now this GV is given as V plus half into WE, omega E, equal to 0, 1, 2, da, da, da. And Fj, this is a recap, this we already know. So this is given as J into J plus 1 dE. So J is equal to 0, 1, 2, da, da, da. On this basis, that how, these terms that we see over here, like this, and this, okay, can produce spectroscopic information. So that is the main goal, that how each of these terms, the electronic energy, rotational and vibrational, can produce spectroscopically relevant information, right? This, how these can produce spectroscopic information. Okay, so we first isolate the various regimes of the electromagnetic spectrum, and these regimes are written in terms of both wavelength or wave number, whatever it is. Okay, but there are certain indicative borders that you will see, but let us first write down the regions. Okay, so this we call it as significant regions of the electromagnetic spectrum. Okay, for molecular spectroscopy. Okay, so first is the region. Okay, then there is the wavelength. Then there is a wave number. Then there are the transitions. Okay. So this is far UV. Okay, in the nanometer, this is in nanometer. This is in centimeter inverse. Okay, so 10 to 200 is far UV. Okay, and the transition is usually electronic. Okay, this approximate once again. So this is written as 6 zeros basically. Then there is near UV. This is 200 to 400. This is done in combustion experiments routinely. Combustion spectroscopy. This is also electronic. I'm just putting Ito sign here. Then of course comes visible. Okay, visible is 400 to 800. Okay, so this is 25,000 to 12,500. This is also electronic. Okay, then of course there is near IR or infrared, which is between 800 to 3,000. This once again in nanometer. 100 to 00. This is vibrational, but it is overtones. We'll come to that. What is overtones? Okay. Then of course there is the mid IR, which is 3,000 to 30,000. Okay, in terms of the wave number, this is about 2 to 300. This is once again vibrational, but this is fundamental. Okay, then you have far IR, okay, which is 30,000 all the way up to 300,000. Okay, this is 300 to 30. This is rotational, light molecules. And then there is microwave. Okay, so the microwave is 300,000 all the way up to 500. See if I put all the zeros correctly. 32.2, and this is rotational. Okay, so this is the main regions. Of course, the demarcation is a little tentative in nature. So spectroscopies typically report all infrared, visible, near ultraviolet wavelengths in air. Vacuum wavelengths are used for far UV because measurements in air are not possible below 200 nanometer. So measurements in air are not possible. So below 200 nanometer. Okay, so you report, so the spectroscopist, if you are a spectroscopists, they have to report all values, in all IR, visible, and near UV, okay? Near ultraviolet. Okay? Combustion work usually uses, for example, OH lift type of measurements, we use near ultraviolet. Okay, so these are the different types of the spectrum, and these are the kind of fundamental demarcations that we have. So in a nutshell, let us first start looking at rotational spectroscopy. Rotational spectroscopy using rigid rotor model. Okay, so we begin by considering that the rotational energy modes undergoes transposition with no influence from vibrational or electronic energy modes. So the fundamental assumption is the rotational energy modes, okay, undergo transposition, okay, with no influence from electronic or vibrational modes. Okay, sounds fair and square, I guess. Okay, so the selection rule we know is delta J is equal to plus minus 1. This was the selection rule. So if, say, J is equal to 3, okay, so absorption or emission. So if it is absorption, okay, it will go to J equal to 4, or if it is emission, it will go to J equal to 2. So these are the only two modes that are possible, right? Because J final minus J initial is plus 1 or minus 1. So these are the two things that are possible, right? J equal to 2 or J equal to 4. So in other words, J final minus J initial is equal to plus minus 1. That's the rule. So the potential complexity is kind of reduced. So a convenient method of writing the rotational selection rule can be written as J prime minus J double prime is equal to 1. Okay, the single prime, this refers to upper energy level, and this double prime actually refers to the lower energy level for any transition, whether absorption or emission. Okay? Absorption or emission. Okay? So applying this nomenclature for each spectral line for pure rotational transition. Okay? For pure rotational transition. Okay. E rotation change J prime plus J prime plus 1 into BE, okay, minus J double prime plus 1. Right? Wave number of each spectral line. Okay? Wave number of each spectral line. Got it? Okay. So this becomes 2BE into J double prime plus 1. J double prime is equal to 0, 1, 2, etc. What we have done, we have substituted this expression, okay, this expression over here. Okay. So that gives rise to this. Okay. So if you look at this, say for example, draw an energy level diagram. This is, say, J equal to 3, say J equal to 2, J equal to 4, and this is the pill sitting there, so it is go that way, and of course there may be higher energy levels available, but it is not accessible. Okay. And then there is the ground point, 0 point energy or 0 level energy. Okay, so that so this is what it is. Okay, so that equidistant spacing, so that an equidistant spacing is given by, so that equidistant spacing, so equidistant, so that equidistant spacing, if we look at equidistant spacing, is given as 2E. Okay. So this occurs between, okay, all adjacent line pairs in any rotational spectrum, produced by this rigid rotor. Model. Okay. This is an approximation, but this is simple but powerful prediction. Okay. So also recall that BE is equal to H divided by 8 pi square C into IE, okay, where the moment of inertia IE is given as mu RE square. Okay, so if you try to evaluate the evaluation of BE by using this, okay, to a specific rotational spectrum, results in an experimental value for the moment of inertia. Okay. So thus providing the equilibrium internuclear separation on bond length for any given diatomic molecule. So evaluation of BE, okay, from, you know, this comes from the spectrum. This is spectroscopic information. Right. So this enables us to evaluate. BE, and from BE we can evaluate IE. Okay, and from IE we can find out the equilibrium internuclear distance. We can find out the equilibrium RE, okay, which further gives rise to the bond length, okay, for a given diatomic molecule. Excellent, no? So just by measuring the spectrum, okay, or the wave number of the spectrum, we can get an idea of what is going to be BE. And since BE incorporates IE, which is the only variable here, and IE incorporates the moment of inertia, which is essentially involves the equilibrium internuclear separation length. This gives an idea of the bond length for any given diatomic molecule. Okay. So, but this is an approximate issue because we still use the rigid rotor model, which we know that is not exactly correct. So this particular thing verifies that if you look at BE, that average line spacing, so BE is equal to H 8 pi square CIE. This gives out important information that average line spacing, right? Got it? Average line spacing for rotational spectrum. Spectrum becomes narrower for heavy molecules, right? for heavier molecules. This is given. IE becomes large because mu becomes large. As IE becomes large, B becomes small. So delta B becomes smaller. So the line spacing becomes narrower. As the line spacing becomes narrower for heavier molecules, the lines are more congested. Okay, so and it is broader for lighter molecules, like OH, for example. OH is a lighter molecule. Okay, so but for however the as we saw, the transition dipole moment is 0 for homonuclear diatomics. For homonuclear diatomics, it is 0. Okay, so the obvious result is no rotational signature. No rotational signature for homonuclear diatomics. Okay, for heteronuclear diatomics, or heteronuclear diatomics, okay, the rotational constants, okay, range from 0.1 to 30 centimeter inverse. So these rotational transitions, they appear, this rotational transitions appear here in microwave and IR portions of EM spectrum. This we already saw in the table. So if you have forgotten just the table, just relook at this particular table that we just did. Okay, microwave, RIR, nature of the spectrum. Okay, so this is rather good. So you know that, so the rotational transitions, we now have a very good idea. Now, next comes, of course, the vibrational spectroscopy. Vibrational spectroscopy using harmonic oscillator model. Okay, so harmonic oscillator model, the selection rule, okay, similar to the rotational form. Selection rule is V prime minus V double prime is equal to 1. Once again, V prime corresponds to a higher vibrational energy level. V double prime corresponds to a lower vibrational energy level. Okay, so therefore, similarly, we write wave number tilde given as V prime plus half omega E minus V double prime plus half omega E. Okay, so if you now substitute this into this, okay, you get V prime is equal to omega E. So for pure vibrational spectroscopy, we generate only a single spectral line at the fundamental frequency. So for pure vibrational spectroscopy, okay, we generate okay, a single spectral line at fundamental vibrational frequency omega E. Okay, so we generate only a single spectral line, and if we recall what was omega E, omega E was 1 by 2 pi c k naught by mu, right? K0 by mu. Okay, hence the spectral measurements of this fundamental vibrational wavelength leads to knowledge of the force constant or the bond strength of a particular diatomic molecule. Okay, so the spectral measurement of omega E and omega E, or the fundamental vibrational wavelength, leads to knowledge of the force constant or bond strength, okay, or bond strength for a diatomic molecule, okay, for a diatomic molecule. So typically omega E is equal to 1000 to 3000 in terms of the wave number. So the fundamental vibrational transitions appear in the fundamental vibrational transition. It appears okay, in the mid IR, okay, portion of the spectrum. Okay, so we'll see a little bit more on this, that why vibration also means rotation and stuff like that. But the fundamental vibrational wavelength leads to the knowledge of the force constant or the bond strength of a diatomic molecule. Okay, so in the next class we will see that how this vibration and rotation, they actually kind of coexist. Okay, and that will be the subject of the next lecture. Thank you.